All right. I hope you can hear me. Yes, I'm presenting PyLHE. I'm Alexander Neuwirth, and the idea was to use this workshop as a deadline, so we finish hopefully the version 1 before the workshop, and this night I will release it, hopefully. That's the plan. So I guess not everybody is familiar with the LHE file format, so I decided to start with a really quick introduction. So it's a standardized file format for high energy physics simulations generated by Monte Carlo event generators like MudGraph, POWHEG, etc. And it's used by many different codes, for example, also PyLHE, and it's a nice interface between different stages of simulating heavy ion or proton-proton collisions. The format is XML-based with a weird Fortran mix-in for historical reasons, and the event structures, you have a list of events. So this looks like this then, where we have normal XML structure for LHE files with a header in it and multiple event blocks. The weird thing now is that the data is not in XML structure, but Fortran compatible. It's just numbers separated by space, tab, or whatever. And that's for historical reasons. So old codes can also read this new format. It was new decades ago, but it has served quite well, the field. And the Python interface, PyLHE, has existed for a few years. Now we've done some changes in the last 2 years, I guess, to now finally get to a version we would call 1.0, where we have mostly changed. We have added strict type checking, we have extended our test suite, and we have now official documentation nicely on read the docs. So what has changed? Previously we had just functions that would like read file, and that would return then the passed input. Now we have extended this by a new class, LHE file, where we can pass either from a file or from a file or from a string. And here I have put the simplest imaginable LHE example data of a collision. We see our loaded data input here, and can also visualize our event. So in this case, we have incoming 2 electrons with the Monte Carlo PDG ID, electron and positron collision going in. The intermediate particle is a photon here, and then we split into UU bar and gluon with given momenta and other parameters. This is using Graphless to visualize it in a notebook, which is quite convenient. In the new release, we changed our data structure from dicts to data classes. So previously, having our LHE file loaded, you would access parameters of the LHE file using a chain of dict access operators. And in the new version, we added deprecation warnings for this, in my opinion, ugly way of accessing data. For example, here we access the type of our incoming beam, which was the electron. Now, with data classes, we do not longer have to quote and put brackets around it. It's just a direct member that can be accessed. And also, it's possible to list all the particles. In a convenient way, the data class approach immediately shows us all the properties by default. If you print an object now, the data class always shows all the parameters, which is very convenient. Other stuff that we can do conveniently is, which was not previously possible with data classes, we all know all of the members, so we can just use the IDE or Jupyter notebooks to access whatever we want to access, which is nice. However, if we now print our LHE file, there's a weird effect. We now have a different output than what we read in as a string, which is a result of the way we pass our files. The LHE files can typically get very large, around gigabytes or above gigabytes even. So with many events, it's not really feasible to load all of it into the memory. So we use Python generators and yield the events. So after we accessed our event previously here already, no, here, we picked the one and first object and then eliminated from the generator. So if we now want to print again our LHE file, the event is gone because we have already consumed it. So what is a convenient solution, we can either just wrap the events in a list, then the list operator collects all the events and stores all of them at the cost of consuming a lot of memory. For convenience, we allow now to disable loading it as a generator, and then we can loop multiple times over our LHE files events and also do in-place modifications to the file for convenience. So we can print, and also we transparently allow compression to gzip, because as I mentioned, these files can get very large. So we can use our new function to file for an event, and then in this binder thing, we have a new object now that we can cut, which is exactly the same as our previous input string that we used here. So why did we do this change from dictionaries to data classes? The core principle, I guess, behind it is pass, don't validate. There's a nice linked blog article about that. And the advantage of using data classes is that we can now nicely type our stuff, and we can use MyPy. And for example, in the old way, we used to directly inherit dict for our LHE init class. And then we would set field names and have some, we would forward the arguments for the construction of this object to the superclass. And this is quite ugly, especially given, for example, the object weight group, which would become a dictionary of strings, a dictionary of strings, then a dictionary of strings, a union of string. I think this should be an int. It doesn't, no, it's right. But yeah, it's not very comprehensible. So adding the data classes for this instead of having multiple stacked dicts is very nice. The new layout with data classes, for example, then becomes this construct where we now explicitly can give our init info should be an LHE init info, again, data class. The POC info is a list of process information, and this is a bit weird, but you can actually document members of a class with the information string. For example, for the LHE init info, we can add this init information docked string that will then show up in our documentation for the LHE init. If we go to attributes, we can go to init information, and we see init information is our init information. Very enlightening, but this can go, for example, with the other classes. However, we want to be backward compatible to the pre-version 1 LHE release, pre-LHE releases. So we want to achieve compatibility between data class access as well as dictionary access. And there I constructed a abstract. So this is the Python ABC class, data class, with a mutable mapping from string to anything, which is then again behaving very similar to a dictionary in Python. And we can now write the same Python double underscore operators as dictionary uses. For example, for accessing, setting, iterating over the dictionary using the data class as dict operator, as well as the length, so the number of keys in our dictionary. Also previously we had the property field names. This can be using the decorator property. We can reintroduce that to our files without having to explicitly give the list of field names that our object contains again. And however, there's one thing that dictionary supports that data classes do not, that's deletion. So there we just throw an error that you cannot delete stuff that's always supposed to be part of the data class. Yes, so the next steps are for us to release the version 1, as well as releasing a JOSS paper. Depending on how much time I have left, there are many examples. Okay. Then let's take this one. So we have seen some awkward already during this talk examples. So with PyLHE, we can easily convert the events we've passed from, for example, this SK-HEP test data file of the YAN process to 2 leptons. We can load that, and we construct using the hist package a histogram of these dimensions. We take our LHE file, we load it with attributes. So we want to have some additional XML information that's then also converted to an awkward array. This will take a bit depending on the size of the array, and we get all the events as an awkward array and can fill our histogram. Let me try to, maybe we can even visualize the events now, what they look like. So we have a bunch of event infos with varying size of number of particles per event, and a similar structure to the LHE. So we have a ID, we have a scale, we have couplings, and then each event has different weights and particles. Yes, the plotting using hist is very convenient in this case. This will visualize again what's actually happening in these events. For example, since this is a YAN process, there are different diagrams. We can have a UU bar to dileptons as well directly, as well as through an intermediate set boson to dimuons, which can be here. This can be stored in a PDF using our renderer, such that we should have now here the same illustration exactly. What's also convenient, coming to a second example, is filtering an LHE file. So here I'm again just importing the stuff we need, some plotting routine that's not too interesting. Here's a snippet from the LHE file, what it looks like. And now if we want to visualize a few of the events, now this is weird. Here. This can be illustrated as a plot. And we see the set peak at 90 GeV coming from the data. And now, since we are using generators, we can write our own generator, which filters the existing events. So we first load all of the events, and then we have here our new generator that loops over the loaded events, and only if the one of the particles is a Z boson, we yield the event. So we construct a new LHE file with the same init block that might or might not be necessarily right, since the init block also stores the total cross section, but that's not the point here. And the filtered LHE events, which then is a new generator constructed from the old generator. And this we can use to write to another file that should appear on the left then soon. And comparing this plot, this stops around 55, I'd say, and is quite different to the other one where we did not filter only the Z boson events. Yes, also in the tail we see goes down very quick, whereas here at around 130, there's still quite a lot of background. Yes, I think I'd conclude here then, and feel free to check out more of our examples that we have. Thank you.